Hello students, welcome to the channel Statistical Hub. This is our lecture number 15 in the course SH201A probability theory. So in this particular lecture, we are going to cover something about the hypergeometric distribution. Okay. So this is like slightly different from the other distributions, and we don't have to go for like a lot of things about the hypergeometric distribution. Majorly, we are going to cover like what is the meaning of a hypergeometric distribution. That is the foremost like the goal for this particular lecture. So this will be a very short lecture, just the introduction to the hypergeometric distribution. Okay, so let's start. So the idea behind this thing is like I can frame something. So let's say you are having a particular bag. Okay. In this bag, you may be having like a lot of things. So let's say the complete size of this bag that is containing maybe n number of maybe marbles or something, anything that you can say. Out of these n number of balls, if I say that I am having k number of balls of maybe black color. Okay. And let's say the remaining balls, that is n minus k, they are of white color. So I'm having this bag containing k number of black balls and n minus k number of white balls. Okay. Now in this particular point, what we are going to do, you have to take out a sample of size n. So we have to take out a sample of size small n from this particular population. And the idea is you don't have to go for like the idea is without replacement. So you are going to get these observations without the repetition or the replication. Okay. Now in this particular part, they will say that this X, this counts total number of success out of like in this particular bag. That's the idea. Okay. So what is happening? So the point is in this particular bag, when you take out n observations, we are interested into X, that is a random variable that counts number of black balls. Like in my example. So the point is, if I just go for the definition that is given in the slide, so you are having a hypergeometric distribution that models the number of success in a sample of size n that is drawn without replacement from a population of size capital N. And in this population, it is containing k number of success and n minus k as the failures. So we need to know or we need to get small k number of success in our sample of size small n. So this probability will be like we need small k number of success. So out of the possible number of success, we need to pick small k number of success. Okay. The remaining ones that will be from the failure. So that will be n minus capital K, C, n minus small k. Okay. This is the small k and this is the capital K divided by the total, that is n, C, n. So that is the probability model. Okay. Very simple. Now, in this particular part, what are the possible values of k? So, if you just go for the maximum, then we know if you are having the n, the sample size, if the sample size is less than this capital N, then you won't be having like more than n number of success, correct? Okay. So, we are getting the n. Okay. And on the other hand, if the n is coming out to be less than k, then if you are having only possible k number of success, then we know the maximum can't be like exceeding the value of k. So it will be like less than or equal to the minimum of n comma k, and it will be starting from the maximum 0 comma n minus capital N minus k. So these are the possible values of the x random variable, that is our hypergeometric distribution. Okay, so we are having a lot of parameters in this case. So that is the population size. Okay, capital K is the number of success in the population. Small n is the sample size. Small k is the number of success in the sample. Okay, that is the idea. Okay, let's move ahead then. Then in this particular part, you have to memorize the properties. We are not going for the derivation or something. Just simply go for memorizing these things. So expected value of x that will come out to be n into capital K over small n. So you can simply think, what is this thing? That is just the proportion of success. Proportion of success in population. And we have to take a sample of size n. So the expected number of success will be n into p, the proportion. So that's why it is coming out to be n into k over capital N. Similarly, if you go for the variance of x, that will be n into p into q, right? And we are applying the concept of like the other thing that we have taken into consideration is without replacement. So there is a continuity correction over there for the finite population. So in this particular thing, that is coming out to be n into k over capital N, 1 minus k over n and we are having n minus small n over capital N minus small. So that's the variance. And the probability function we already covered. Moving ahead. Okay, so I'm not going for the derivation or the proof or something. So you can simply see the result is like intuitive, like without solving anything. I was able to write this thing, like what is the expected number of success in this particular setup. So we just got the proportion, just comparing with the binomial distribution, they are getting n into p. So that is the expected value. Okay. And if you go for the variance part, then this formula adjusts for the fact that the sampling is done without replacement. And due to this particular thing, the point is the very next success that you may be getting, that is depending on the previous trials, right? Assume that like in the earlier trial, you got like a success. So now in the back, you are left with capital K minus one number of success. And out of these, I'm going to get one success. So it is changing, and due to the introduction to the dependency, the variance of X that will be coming out to be this thing. Okay. Then we are having some examples that you can think over, like in this particular example. So the problem sets that we may find the hypergeometric distribution will be part of this thing. So if you go for the first example, that is the number of defective items in a sample from a batch. So if you go for this particular example, then you know in the complete batch, there will maybe k number of defective items and capital N minus k number of non-defective items. And we have to count total number of defective items in our sample of size n. Like you won't be checking like the complete batch, but any like quality inspection, they just go for this one thing, that from the complete sample, the complete population, the complete batch, they're going to take out maybe n observations, a sample of size n without replacement, and then they're checking how many defective items they are finding. Correct? So that is an example of hypergeometric distribution. Or this kind of setup can be arranged using the hypergeometric distribution. Okay. Then we move to the second example, that is the number of red cards in hand of a card drawn from a deck. Again, the same thing. In the deck, you may be having multiple cards. You may go for maybe 26 cards that are red, and the remaining 26, they are black. You can count this to be the success, this to be the failure. So if you are taking out a sample of maybe 10 cards, then out of these 10 cards, there can be some success, there can be some failure. Again, a hypergeometric example. Okay. Then the third example that we can see is the number of students with scholarship in a selected group of class. Again, the same thing. So if you pick out maybe some students in a class, then some students may be having some kind of scholarship, other students may not be having the scholarship, right? So these are again some examples of the hypergeometric distribution. Moving ahead. Okay. Now this is one of the example of maybe some problem that we can see over. So we are given a batch of 100 items. So you are having the capital N that is given to be 100. Okay. And it is containing 10 defective. So out of 100, you are having 10 that are defective. So that can be taken to be the capital K. And you are left with 90 that are non-defective. So if they are non-defective, that will be counted to be 100 minus the K. So that is N minus K that we are finding. Okay. And if 15 items were selected, so you are taking out a sample of size N, that is 15. What is the probability that exactly 2 of them are defective? So very simple, small k that is coming out to be 2. So we need to get probability x equal to 2. So we need to get 2 success out of n, that is k in our case. So that is 10C2, the remaining 90C13. We need total 15 divided by 100C15. So if we solve it, you are going to get 0.235. That is the probability that we are getting. So very simple concept. In this case, if you have to find the mean, you can simply find n into k over n. If you have to find the variance, apply the variance formula, you'll be getting the variance also. Okay, very simple concept. That is the basic idea about the hypergeometric distribution. If you go for application, so all the examples that we covered, they were majorly about the quality control. So you can go for the quality control. And it is used in ecological studies for estimating population parameters. Okay. The example can be like estimating the number of certain species in a habitat. Okay. So in a particular place, if you go for, then if you have to get an estimate, so out of the complete population, maybe we are going for maybe some particular kind of cobra in a particular habitat. So we may be interested in like finding different snakes. So out of maybe 100 population size, we are taking a sample of 10 and we are finding one cobra. So on the behalf of that one, we may be estimating the number of certain species in that particular habitat, or maybe any similar kind of thing. Okay, so that was something about the hypergeometric distribution. Again, if I just go for a recap, which is a bag with k number of success, n minus k number of failure, and you need to get a sample of size n. So we are getting x, that is the number of success in the sample of size n. So that is simply, you are going to get kc x, and the other will be, we are getting like the x, the number of success. So the remaining will be coming out from n minus k, c, n minus x over, we have n, c, n. Very simple. The basic probability rules, and that is the definition of the hypergeometric distribution. So that's what you have to understand about the hypergeometric distribution, and you can practice a lot of problems that will get you an idea like how to apply the hypergeometric distribution. I hope you're able to understand the concept of hypergeometric distribution. So that's all in this particular lecture. Thank you. Bye.